Okay, so last time we began to learn about the physics of dipoles. Let me remind you what a dipole is. Dipole is two charges, a negative charge, that I'll put right here, and a positive charge that I'll put right here. And by convention, we are going to refer to the separation between the two charges as 2a. So this distance here from one charge to the other, we will call 2a, a being some quantity with the units of length. And what I want to do now as the first step towards doing a quantitative analysis of the physics of dipoles, how they move, what forces they feel, what torques they feel, is I want to introduce a quantity called the electric dipole moment, which is a measure of the strength of a dipole. And I will introduce it in the context of an arrangement of charges, which is simply the simplest possible case where there is a dipole moment, which is two charges, a negative charge and a positive charge. I'm going to refer to this lower charge, this negative charge, as Q1, and Q1 is negative. So I will think of Q1 as minus Q, Q being some quantity of charge. And this upper charge here we'll call Q2. Q2 is positive, so Q2 will be plus Q. So I'm choosing a configuration of charges in which the magnitude of the two charges are the same. Their signs are opposite. This one is positive, this one is negative. They're separated by a distance 2a. And we can now define the electric dipole moment, which is represented by a vector p. So this is the electric dipole moment. And its definition is, for a case like this with only two charges, its definition is simply Q1 R1 plus Q2 R2, where Q1 and Q2 are the two charges. I've already told you what those are. But now what are R1 vector and R2 vector? R1 vector and R2 vector are vectors from the origin to charge 1, from the origin to charge 2. Well, what origin? As I will explain at the end, it doesn't actually matter where I put the origin. But for simplicity and convenience, I'm going to put my origin right there, right in the middle between the two charges. And I'm going to pick a coordinate system now. I'm going to pick my x-axis to run this way, my y-axis to run this way. And that means that I have, in terms of unit vectors, I have a j-hat vector that points up and an i-hat vector that points this way. So with that definition, I now can draw my R1 and R2 because I've picked an origin. R1 is the vector from the origin to charge 1. So this is R1. And R2 goes from the origin to charge 2. So this is R2. And once I have these definitions, I've got R1, R2, Q1, Q2, I can now evaluate the electric dipole moment of this configuration of two charges. So it's Q1. What's Q1? Q1 is minus Q times R1 vector. What's R1 vector? Well, R1 vector is a vector whose length is a and whose direction is minus j hat. So I have a and then a minus j hat plus Q2. What's Q2? Well, Q2 is plus Q. What's R2? R2 is a vector that points in this direction, so it's in the plus j hat direction, and once again it has length a. So I have Q, a, j hat. And you see two minus signs here, minus minus, that makes this plus, so these two terms add. And so we end up with an electric dipole moment given by 2 times Q times a times j hat. And this is, in fact, our result for the electric dipole moment of this very simple configuration of two charges, one positive and one negative. And what do we see in the result? Well, we see a vector that points from the negative charge towards the positive charge. It's pointing in the j hat direction. That's this direction here. So the dipole moment vector always points from the minus charge to the plus charge. And what is the length of this vector? Well, it's Q. Q is the magnitude of the charges at the two ends. times 2a. 2a is the separation between the two charges. And so this generalizes. If I have some other dipole over here, here's my negative charge, and here's my negative charge, and here is my positive charge, then the dipole vector for this dipole will be a vector that points in this direction. And the magnitude of this dipole vector, electric dipole moment, the magnitude of this dipole moment will be given by Q, which is the magnitude of the charges at the two ends, times this separation between the two, and the separation between the two we are going to be calling 2a. 2a again being this distance here. So last point, I said it didn't matter where I chose the origin. Let me just convince you of that. So suppose I had been perverse and made my life difficult by choosing my origin here. Why on earth would I pick the origin there? Well, I just want to show you that it doesn't matter. If I had picked my origin there, if I'd been made my own life difficult by doing that, I'd have a new R1. This would be my new vector R1, and I would have a new R2. This would be my new vector R2. But if you look at what occurs in the expression for the dipole moment, it's Q1 R1 plus Q2 R2, but Q1 and Q2 have opposite signs. So the vector that comes in here is the vector given by R2 vector minus R1 vector. So when I go back over here and I do R2 vector minus R1 vector, that gives me a vector which connects the tips of these two and points in this direction. So no matter where I had picked the origin, I would have gotten the same result for the electric dipole moment. I would have gotten, for this particular configuration, I would have gotten 2qa times j hat, even if I had put the origin there and made my own life difficult. So the electric dipole moment can be defined for configurations with more charges. This definition generalizes. You will have Q3 R3 plus Q4 R4 dot, dot, dot. And you'll see that next. But this is the simplest case with which to introduce this definition. And so for today, we will stop here.